Okay, so let's start off with the Mandelbrot set example and the first exercise, which is to program it just with using a parallel region and not any work sharing directives. Okay, so I hope that is readable for you all. Let's see if, yes, it will all fit on the screen. Okay, so for this example, okay, so what we need to do is enclose the whole of this loop nest inside a parallel region. So hash pragma OMP parallel at the top, and then everything inside pair of curly braces. Let's see if I can deal with a pointer here. No, I can't get a pointer here. Okay. Can you see my mouse? Ah, fantastic. Okay, so it's not very, I know it's not very big, but hopefully I will point at stuff then, and it should work. Okay. Okay, so parallel region. Take my own advice. Okay, and specify default none, but I'll come back to discuss the data attribute sharing clauses later on. Okay, so in this case, what we need to do is explicitly calculate which loop iterations each thread is going to execute. Okay, so instead of, and I'm just going to parallelize the outer I loop here. So instead of I running from 0 up to endpoints, I'm going to create these variables, my start and my end, for each thread to calculate its loop bounds in. Okay. So to do that, I need to first of all get my thread ID. Okay, call OMP get thread num, and then I also need to know how many threads there are in total. Store that in n threads, and then to calculate how many points each thread is going to work on. So this is just a little arithmetic trick to do the division but round up. Okay, so this is really, it's just doing, all I'm doing here is dividing endpoints by n threads, but I want the division to round up rather than round down, which normal integer division will do. So points per thread is just equal division of the points across the threads and round it up. Okay. So then I can now calculate my start and end points. So start point is my thread ID times the number of points per thread, and then my end point is going to be my start point plus the number of points per thread. But then I have to take care about the case where the endpoint might overrun the end of the loop. So just adjust the endpoint so that it doesn't exceed the end of the loop. So now I've calculated for each thread which loop iterations it's going to execute. So I can use that to split up the iterations of the I loop between the threads. Okay, so let's just go back to looking at the data attribute scoping. So in this case, so all these things I've declared, all these variables, I've declared them inside the scope of the parallel region. So all of these variables here will be private by default. As will the loop iterators, so I and j and iter, and this temporary variable ztemp, So these are all declared inside the scope of the loop. So those are all going to be private by default. And it's in fact not possible to list those things in the private clause because those things are not in scope when the parallel region is encountered. So if you try to list those things inside the private clause, the compiler will complain and say, oh, okay, there's no such variable at this point. Okay, so things I do have to care about that are declared outside are these complex structures Z and C. Okay, and you think about it for a little bit. I really want every thread to have its own copy of that because every thread is going to initialize C and Z in these lines here. And then use them and use Z in this loop, and then use Z and C in this loop, and then that copy's done. That's done with, and then we reinitialize them again. Okay, so they really act as temporary variables inside the I and J loops. So we clearly want every thread to have its own copy of that. Otherwise, we would end up with arrays. And then the final variable I have to care about is num outside. Okay, so the variable that's counting the number of points outside the set. Okay, so that gets incremented here. So the easiest way to deal with that is as a reduction. So that's a classic reduction pattern. So it's just forming a sum. It's initialized outside the parallel region somewhere. Yeah, right up at the top. So we can treat that as a reduction variable. So just to remind you what's happening here, every thread gets a private copy of num outside. Those private copies will be initialized to 0 because we're using the addition operator. This increment then is done by every thread on its own private copy. And then when we get to the end of the parallel region, those private copies are summed into the original storage for the variable, including the value in the original storage, which, well, happened to be 0 in this case, so it didn't make any difference. And that's how we get the final sum out at the end. There is an alternative here. So didn't expect you to look into this, but having num outside shared and then doing an atomic update here using hash pragma OMP atomic on the update here will also work. That's also correct. It's potentially less efficient. And in this case, the updates to num outside are relatively infrequent, probably compared with the amount of computation that's going on in this loop. So it probably will perform okay, but in general, for this case, it's likely to be better to use a reduction, and then that avoids any synchronization happening between threads until we get to the very end of the parallel region. And reductions are usually implemented pretty efficiently. It's actually possible to fold them into the barrier that happens at the end of the parallel region. So they do add a little bit of cost to the barrier at the end, but it's certainly for a scalar variable, it's a pretty small additional cost. Okay, does anybody have any questions about that? Okay, so if you did some performance measurements on this, you probably find that it doesn't, you don't get perfect speed up. And the reason for that is that this loop, in fact, neither of these loops are well balanced. And the reason for that is that depending on the value of C, then this inner loop, this iteration loop, may take different numbers of iterations before it breaks out, or it doesn't, or it doesn't break. So typically what you find actually is that for points that are outside of that set, it only takes a small number of iterations before the break happens. Whereas obviously for points that are inside the set, you have to go the full max iterations. So if we're dividing up, think about dividing up the box in the complex plane into strips based on the I value, then so that's basically so I value is indexing the real part. So yeah, so we're basically doing vertical strips across that box. Some of those strips will include much larger parts of the Mandelbrot set than others. And so the ones that include more of the Mandelbrot set will have a heavier load on them. So this is not naturally very well load balanced. So a quick look at the Fortran version. Okay. It's essentially the same. The only real difference is that all these variables that I've introduced to calculate in order to be able to calculate the loop bounds, so they have to be declared at the top of the routine and listed in the private clause here for Fortran. But otherwise everything is pretty much the same. Okay. So you'll have realized I was kind of mean to you to make you program that version first. But I think it's important to do that so that you really understand what the semantics of parallel regions are. They really are. It really is just every thread executes the block of code inside the parallel region. Okay, so clearly the most sensible way to solve this problem with the features we have available to us in OpenMP is to use work sharing. And so this is one of these nice cases where we can do everything with just a single directive here. Okay, you don't have to modify the original sequential code at all. So in this case, we can use the combined parallel for convenience. So again, default none, Z and C are private, num outside is a reduction, and then the work sharing directive gives us the opportunity to solve the load balancing problem. Okay, so actually this is kind of an easy problem in a sense that there's an awful lot of work. The execution time inside iteration of the I loop is really quite big. So that means that the overheads, any overheads that are incurred with the choice of schedule clause are pretty minimal in this case. So pretty much anything sensible, any sensible choice other than static will do a decent job of balancing the load here. So I've chosen dynamic 1, but that's you won't see a great deal. If you choose static with a small chunk size, dynamic with a small chunk size, or guided, will all do a pretty decent job of balancing the load in this case. Okay. Any questions about this one? Okay, so again, let me just show the Fortran version. So absolutely no surprises here. So perhaps one thing to note is to do with the private variables here. Okay, so I don't need to list I and j as private variables because in Fortran, the loop iterators, so do loop iterators like this are always private by default. So in either Fortran or C, the parallel loop iterator, so in this case, I is private by default. But because this is Fortran, J is also private by default here. On the other hand, iter is not iter is just a regular variable. It's not a do loop iterator. So I do have to declare that in the private clause. Okay. So while we're at it, while we're talking about the Mandelbrot set example, let's look at the case with nested parallel regions. Okay, so again, for this particular example, it doesn't make a whole lot of sense. So for the example I've given you, but if you say had fewer, if endpoints was a bit smaller, and you wanted to try to run this on, say, 128 threads, then eventually we get to the point where it probably isn't actually possible to get load balance just by parallelizing the outer loop. And so you could perhaps consider doing nested parallelism. Again, this wouldn't be the best choice for this example. It would be better to use a collapse clause, which I'll also talk about as well. But if we did want to do nested parallelism, then this is how it would work. Okay, so we would have a parallel for on both the I loop and the J loop. So what's going to happen is, in that case, we're going to choose a certain number of threads to execute the outer parallel region. The iterations of the I loop will be shared between those threads according to whatever schedule we choose. And then for every iteration of the I loop, we're then going to have an inner team of threads which will share out the iterations of the J loop between them. Okay, so there's potentially quite a lot, there's potentially more overhead here because we are creating this inner parallel region lots of times. Okay, so this inner parallel region will be created, and the synchronization at the end has to happen a total of endpoints times, spread across the threads in the outer region. Okay, so that's reasonably straightforward. The slightly tricky thing here is working out what happens with shared private and reduction variables. Okay, so let's think about these in turn. Okay, so Z and C, we still want, those are only accessed inside the J loop. So we still definitely want every thread in the inner parallel region to have separate copies of that. Okay, so I should definitely declare that private on the inner parallel region. It actually doesn't matter what I do on the outer one. Either shared or private here is at this point here is correct. Okay, because those variables are not are only referenced inside the inner parallel region. They're not referenced directly by the threads in the outer parallel region. So it doesn't matter whether they're not going to use it, so it doesn't matter whether they have a private copy or a shared copy. But the inner ones definitely need a private copy. Then what else do we need to deal with? Okay, we now need, for the inner parallel region, we now need to think about I. Okay, because I is in scope when the inner parallel region is created, and it's going to be, because it's declared here, every thread in the outer parallel region has its own copy. But we actually want threads in the inner parallel regions to see the same copy of I. Okay, so the current value, we want them to see the current value of I. And so it's the way we can arrange that is to make I shared on the inner parallel region. Okay. So this gets a little bit complicated to start reasoning about. Okay, so I is private with respect to the threads in the outer parallel region, but it's shared with respect to the inner parallel region. So this shared means use this thing here. Okay, so if you like, when we get to nested parallelism, a useful way of thinking about what shared does is it says use the existing storage with that name, okay, and don't create any new copies. And we also have to think a little bit carefully about num outside as well, the reduction variable. And so if you think about that for a bit, you realize that you need to have the reduction on both the outer and inner parallel regions. But think about what does that do? Okay, so we're going to get a copy of num outside, a private copy for every thread in the outer parallel region. Okay, that'll be initialized to 0. We then get a copy for every thread in the inner in every instance of the inner parallel region. And that sum will be formed at the end of the J loop. Okay, and where does that sum go? It goes into the private copy for the thread of the outer parallel region. Okay, so once we get to the inner parallel region, the original storage that's being used for the reduction here is actually the private copies created for the outer parallel region. Okay, so for the inner parallel region, every thread sums into the private copy for the outer parallel region, and then at the end of the outer parallel region, then those private copies get summed together, and we finally get the complete sum that we need. So that takes a little bit of thinking about as well. And then for the schedule clause, again, we need to think about where's the load imbalance coming from. Well, actually, there's load imbalance in both loops. Okay, so neither the I loop nor the J loop is naturally well balanced. So we have to take care of choosing a schedule kind for both of them. Okay, might not be the optimal choice. You might want to experiment a bit more in this case to figure out what good choices of schedules are. I say probably doesn't matter whether you do static or dynamic, but chunk sizes other than 1 might be better. So you can see that with nested parallelism, reasoning about private, shared, and reduction gets a little bit more complicated. So that's just another reason why I would recommend you always use default none. Make sure force yourself to think carefully about how all these variables need to be declared in these clauses to get the behavior that you want. But in this instance, it really doesn't make sense to use nested parallelism because we would have the collapse clause available. So we could just use that. On the plain case here, we could just add collapse 2 on here. So that what the compiler will do is combine the I and J loops into a single loop of length endpoints squared, and it'll then parallelize that and schedule that. So again, because now we're dealing with much smaller the individual loop iterations, that we've now got a lot more of them, and they contain less work. So it might be the case that we want to experiment with larger chunk sizes larger than 1 to avoid incurring too much scheduling overhead. Okay, any questions about that? Okay, so the Fortran version is essentially similar. Okay, it's nothing different going on here. So again, we've just got this extra private variable to deal with, but that's handled in the same way. Okay, are we all happy so far? We're all being very quiet this morning. Great. Okay, so let's move on to the molecular dynamics then. Okay, so we want to focus on the computation inside this forces routine. So this is not too much more complicated really, except that we have this problem of trying to solve with the synchronization. So again, I'm just going to parallelize the outermost loop here over I. You can use a parallel for, use the combined directive for this. Again, default none. Then I have to go through and just figure out what the data attribute scoping should be for all the variables. So there's a lot of things which are temporaries inside the loop, so which are all private by default. But then there's a bunch of other variables being used. Okay, so might need to think about that for a while. There's a bunch of them, so things like X and NPart and side and side H and arc_s are all read-only inside the loop, so they're not being modified. So that's an easy decision. We just make those shared, which again says, just use the existing copy. We're not going to touch it anyway. Just going to read it. So that's absolutely fine. The other things we have to care about are these variables, vir, the virial, and epot, which is the potential energy. So those are, if you think about these for a while, okay, you see that they are initialized up here at the start of the function. They're then added to, or in the case of the virial, subtracted from inside the loop. And these are actually global variables, so they are then used elsewhere in the code. Okay, so we need the result of those sums elsewhere in other functions. So again, that's just a classic reduction pattern. They're plain old scalar variables. They're just doubles. So we can treat those as reductions with the addition operator. Okay. There is a slight quirk in OpenMP which allows subtraction as a reduction operator, which really doesn't make any sense. Okay, it's kind of a historical thing, really. Okay, because subtraction is not an associative operator. It matters what order you do subtractions in. Okay, so for as a reduction operator for OpenMP, subtraction is actually just a synonym for addition. So that's just kind of weird, right? Why did that happen? So the original intention in OpenMP was to make the compiler check that what you were doing with those variables inside the parallel region actually matched the operator that you specified in the reduction clause. Okay, so the original idea in OpenMP was that the compiler would see, okay, VIR is being subtracted here. Okay, there's a subtraction here, so the compiler should recognize that and complain if you didn't use subtraction operator in the reduction clause for that variable. I've no idea why anybody thought that was a good idea, because it clearly doesn't work for a number of reasons. So it would be perfectly fine to have a mixture of additions and subtractions inside the loop. You don't have to have one, not limited to one reference to those private copies. And anyway, you might pass those private copies down to called routines, in which case the compiler can't see what you're doing with it and can't check. And then thirdly, it doesn't really make any sense to impose that restriction on programmers. You can do what you like with those variables. You don't have to do additions or subtractions. And it gets even worse with max and mins, because there are different ways of calculating max and mins without using the well, you don't even have intrinsics in C for that. You usually just use macros or whatever. So on a number of levels, it absolutely made no sense. So if you do happen to wonder why it's in the specification, then that's the reason. It's a synonym for addition, and you can completely ignore it and never use it. Okay, so then the final variable that we haven't discussed here is F. So the array of force, the array where the forces are actually going to be accumulated. So we have to do something because of the pattern of accesses here. We've got accesses to F, J plus 1, and J plus 2 inside the inner loop, and also accesses to Fi, I plus 1 and I plus 2 inside the remainder of the outer loop as well. So we need to do something sensible with that. And one way to do that would be to enclose those in critical sections, so that only one thread at a time can do that. Okay, and we do. It's not immediately necessarily obvious why we need two critical sections here, because we're parallelizing the I loop, so different threads are going to have different values of I. So why do we need this second critical section here? And the reason is that the value of I on one thread may be equal to the value of J on a different thread, which is executing a different value of I. Okay, so this access here and this access here can potentially conflict. and refer to the same element of F coming from different threads. So we do really need both critical sections here. Okay. So F is shared, and then all the accesses are protected by critical sections, so that only one thread at a time can update F. Okay. Did anybody try that and see what the performance was like? Okay, so if you do, what you'll find is that the performance is poor, and it really doesn't scale very well. You'll see a little bit of speed up. If you go from 1 to 2 to 4 threads, it'll get a little bit faster. But then as you go to like 8 or 16 threads, it starts getting slower again. So the contention for the critical region really kills this one. So we can do better than that. Oh, Felix says, that's what I saw. Okay, great. So we can do better because we could simply use, so one way of doing better is simply to use atomics instead of criticals. And that should, if you do that, then you should see significantly better scalability. And the reason for this is largely because this is one of these cases where using atomics allows different threads to update different elements of F at the same time. And then, okay, let's just briefly talk about the Fortran versions. Oops, wrong file name. The only real difference in Fortran is that you end up having some you end up having this long list of private variables for all the loop temporaries. But apart from that, there's no difference. Okay, Jason says you got some compiler-dependent errors that were fixed with end atomic. Oh, okay. Which compiler? Is that Cray compiler? G-Fortran and G-Fortran with score P wrappers on. Okay, that's a bit weird. If you want to share your code, if you want to send your code to me, I'll happy to take a look at it and see if I understand what's going on there. But it may just be a compiler weirdness. So Felix said he tried atomics and locks. Minor difference, atomic being slightly faster. Is there a major advantage to one over the other? That's kind of probably what I'd expect in this case. So the overhead of atomics is probably a bit smaller than locks. It's a bit compiler dependent. It also depends a bit on the underlying hardware as to what it supports in terms of atomic instructions. So it also depend a bit on. It might be a bit more dependent if you are doing integers rather than, say, if you are handling integers rather than floating point, because some hardware has inbuilt atomic increments for integers, but probably not for floating point. So it depends on the underlying hardware and what's available in the instruction set. But even if the compiler isn't directly able to use atomic instructions to do the update, it's still typically able to generate code which is more efficient than calling a lock. So I guess that's kind of what I expect. If you were in a situation where the overheads were perhaps more important than this one, then you might see a bigger difference. Jason said, also got compilers. Some have an error, forgot to list endpoints as shared and some not. Okay, so end part, yeah, okay. So that might be to do with whether, because end part is so in the Fortran version, it's a parameter in the main program. So if this function gets inlined, then you might get away with it. But in principle, you should need it because as far as this, as far as this function is concerned, it's just a regular integer. Okay. The fact that it's declared as a parameter and then passed in doesn't change that. But it might mean that if the compiler manages to inline forces into the main program, then it also does the parameter substitution for all of the references inside here as well, and therefore you get away without it. So Anthony says, could F be private and avoid the critical atomic parts? So the answer is no, because we care about, well, potentially we care about the initial value of F that's being passed in, and that F is going to be, and we also care about the final values, which are going to be used elsewhere in the program. So if we made F private, we just get uninitialized copies, which we're adding into, and then they get blown away at the end of the parallel region. However, we can treat F as a reduction array. So this is the yet another possible option here. So let me go back to the C version. Okay, so yet another option here is instead of using atomic or criticals, is to put F in the reduction clause, like this. And because it's an array, we have to use this special syntax to specify the start element and the extent of it, because otherwise basically the C component, because it's C, it's all it knows about F is its address, is the address of the starting element. So the compiler can't on its own determine how big F is, and therefore how big to make the private copies for each thread. So that's why we need this this special syntax here. And so, okay, yeah, is this faster than atomics? And the answer is it depends. Okay. In this case, I think it's a little bit faster, but not much. But in general, you can't tell. It depends on the pattern of accesses to F. Okay? So if the parallel loop does a lot of updates to all or most of the elements of F, then having private copies is probably the best option. So doing it as a reduction and having private copies is probably the best option. On the other hand, if this array is big and the updates are infrequent and maybe don't touch the whole of the array, then atomic might be better, because then we're not paying, because the cost of the reduction is doing this, is doing the sum for every single element of the array at the end. Okay, so if the array is large and most of the a lot of the updates didn't happen, okay, from a lot of threads didn't update parts of F, then we basically end up paying the cost of adding a lot of zeros together at the end. So it really depends on the access pattern and the way that the array is used as to whether reduction or atomics is going to be useful. And another problem with using reduction is, again, if the array is large, then you're potentially using a lot more memory. Okay, the memory overhead of having a private copy for every thread might be important. It might say, affect your cache behavior somewhat. Okay, it's one of the cases where you can run out of stack space. Okay, you can, there are ways to fix that. But the extra memory overhead in some circumstances might be important. So this is really typical of this sort of pattern, is that you have this choice between essentially doing a reduction, making private copies and doing a reduction, or having a shared copy and doing atomic updates or critical sections. And you can't really determine a priori which is going to be better for a particular case. Okay, what have we still got to talk about? We've still got to talk about the orphaning case, and potentially also about the ADI exercise as well. So I think we'll take a break at this point. So let's resume at 11. Okay, welcome back. So going to finish off by looking at the version of molecular dynamics using orphaned work sharing. So just to make clear that this is not going to make any significant difference to performance in this case. It's really the point of doing this is to illustrate how variables behave when we have functions or subroutines called from inside parallel regions. So in this case, what I can do, for example, is to move the parallel region out from inside the forces routine to outside. Okay, so in this case, I'm just going to do this the simplest thing, which is have a parallel region which consists of calling the forces routine and nothing else. So that's what I've got here. So this is in the main program. I'm inside this this loop, which is basically the time stepping loop, and then there's other functions being called inside here, other routines being called inside here. There's do move and make ekin and other bits and pieces going on inside this loop. So if I do that, then I just have to take care of the of the variables which are referenced here. So again, this is just x, f side, and arc off, and I just want all of those to be shared. So I just want to essentially just pass the original storage for all those things into forces. Yeah, and sort of with respect to that, or picking up on that previous discussion, n part at this level is in the C is not a variable. Okay, it is hash defined. So somewhere or other at the top. Okay. Way up the top. Yep. Okay. So n part is just is hash defined. So it's not as far as OpenMP is concerned, as far as the compiler is concerned, it's not a variable. And so if you try and list it in a shared clause or private clause, the compiler will complain at you and say you can't do that. The reason for that is that the compiler part, so what the compiler does very early on in the compilation process is basically just to do substitution for hash defines. Okay, so wherever we've got the thing that's hash defined, it just replaces with the compiler will just replace that with the numerical constant, and that happens very early right at the beginning of the compilation process. So it's happened already by the time the compiler tries to interpret the OpenMP directives. So when it comes to interpreting the OpenMP directives and the clauses, n part has already been replaced by a literal constant. So there's nothing here to be shared. Okay, so let's look at what's going on inside the forces routine. Okay, so now we have to remember that this is being called by all threads inside the parallel region. So as far as the loop here is concerned, we no longer have a parallel region here because we've moved that outside. So all we're left with inside here on the loop is the work sharing for. And everything else, okay, disappears. Okay, so we can't have default none here. Everything that's passed in is shared. What we still need here is the reduction clause. Okay. Because, well, why do we need the reduction here rather than on the parallel region? And the reason is basically because of this initialization happening here. Okay, so the initial values of VIR and EPOT are made inside the forces routine. So we could, in principle, move that initialization outside of the parallel region, and then do the reduction on the parallel region. That would potentially be possible. But to minimize the changes to the code, then we can do the reduction at the end of the parallel loop here. Okay, so as far as everything else is concerned, then we have to think about, because now everything is being executed by every thread, we now have to think carefully about these statements that come before the loop. Okay, so we've got these two statements which initialize the reduction variables. So this is an instance of this subtle race condition problem, which I talked about on Tuesday. Okay. So if we didn't have the single here, then every thread would be setting the initial value for these variables. And that can cause a race with the implicit write that happens at the end of the loop to form the reduction. Okay, so the version of VIR and EPOT so the original storage will be modified implicitly by the reduction operation that happens at the end of the loop. So the important thing to recognize here is that the threads do not synchronize on entry to the work sharing. They only synchronize at the end. So there isn't a barrier at the beginning of this loop. So what that means is, just to recap, what could happen is, if we didn't have the single here, one thread could set, say, VIR to 0, and then go all the way, carry straight on into the loop, execute its loop iterations, and then potentially write its contribution to the reduction into the original storage for VIR. And then at some point later, another thread arrives. Okay, so the timing may look unlikely, but we have to protect ourselves against, any possible interleaving of executions. So, and what could happen is that another thread, which is late for some reason, okay, turns up late, and it then resets that value back to 0 again. So the contribution from one or more of the threads could potentially get lost. So in order to do this correctly and safely, we have to both get one thread to do this initialization and also synchronize the threads afterwards to make sure that none of the threads enter this loop until this initialization has happened. So a single is a convenient way of doing this. We could also use master and an explicit barrier here. That would also work just fine. We also need to think a little bit carefully about these other two statements here, which set values inside H and ARCHER2. Okay. Because now that in the original version where we had a parallel region here, these things were being these statements were being executed by the master thread, and these variables were shared. Okay, we had to declare them as shared on the parallel region. So there only was one copy of those things. But now now we're inside. Now we call forces inside a parallel region, and we declare these variables in this function. Then the rules of the OpenMP scoping rules say that every thread gets a private copy of these, and that's still okay because every thread is these are read only within inside the parallel region, but we now, because they're private copies, we do want every thread to initialize their own private copy. Okay, otherwise we would end up with uninitialized private copies. So we do that. It is actually correct for every thread to execute this initialization because they are now private to the threads. So again, once the use of orphaning, and when we're calling routines inside parallel regions, that again makes reasoning about shared privates and reductions just a little bit harder. You have to think a little bit carefully about what's going on here. So another possibility here would be to declare these as static, which would mean that they were shared, and then have one thread do the initialization. So declare them as static inside this routine, and then put the initialization in a single along with these ones. That would also work. Okay. Does anybody have any questions about this one? There's no real differences in the Fortran. There's a slight difference just in the way the code's written. Okay, so in the Fortran version, VIR and EPOT are actually passed in as arguments, rather than they're not global variables in Fortran. And in terms of what's going on in the forces routine, oops. Would help if I had consistent naming conventions, which I don't. Okay, it's the same deal. Okay, so again, because the slight difference, VIR and EPOT are declared as shared on the parallel region. They're passed in. So again, we need only one thread to initialize them, and we need the synchronization afterwards. And similarly, side H and ARCHER2 are declared inside here, so they are private. Okay, so everything that's declared inside here is private to the thread. So every thread needs to initialize these values. So kind of the nice side effect in Fortran, I guess, is that where we previously had a big long list of private variables, we don't need them anymore because they're all declared inside this the forces routine subroutine, so they all become private by default. So this is a case where we use the language, the default scoping rules, and avoid having to have this long list of private variables in Fortran. Okay, any questions about that? Okay, so anybody get as far as doing the ADI example? Okay, so Felix is asking, does the use of orphan routines depend on the use case or philosophy? So it really depends on the use case. It really depends on how your code is structured, and what makes more sense from a kind of software engineering point of view. But it's quite a common. It's not an uncommon pattern, say, to have, in the original code, to have, say, perhaps a more a more common use case would be you have a loop that you want to parallelize with OpenMP, and the loop contains function calls. Okay. And so you then have to think about, okay, what's happening? So you might not necessarily have OpenMP directives inside those called routines, but you still have to worry about whether the data scoping. Okay, you still have to think about what's happening in terms of shared and private, particularly if the called routines are referencing global variables, or have static or save variables inside them. Then you still need to think carefully about how the whole shared, private, and reduction variables are going to work with the called routines. Or you might need some, you might not need work sharing inside those routines, but you might need other directives. You might need synchronization directives like criticals or atomics or explicit barriers or something like that inside the called routines. Okay. Okay, so let me just talk a little bit about the ADI example, even if nobody's managed to get round to it, which I kind of didn't really expect you to. That's absolutely fine. But just to explain talk about what the interesting points are anyway. Okay, so just talk through the code a bit in case you have, those of you who haven't had a look at it. So basically what this code does is, it starts off, it initializes, there's some 2D arrays, A, B, and X. Starts off by initializing those arrays. Then it goes into an iteration loop, and that iteration loop has a couple of loop nests inside it. And it basically ends up calculating some, basically does some convergence test calculating some maximum difference between some values. Okay, doesn't really matter to. I mean, it's based on ADI method. It's based on the pattern that you get in these alternating direction implicit methods, which is, but it's not. This code isn't really actually doing anything useful. It's kind of cut down to the point where it's not actually solving anything interesting. But the interesting thing about this case is to do with dependencies inside loops. Okay, because this is a case where not all of these loops are parallelizable. So the initialization loops are fine. Okay, so these are trivially parallelizable loops. So we can just do OpenMP parallel 4 on the outer loop, and that's perfectly fine. Okay, but when we come to look at these inner loop nests here, okay. Oh, I should say first say first. Then this iteration loop isn't parallelizable. Every loop iteration depends on the results of the previous one. Okay, so this loop has to be executed sequentially. So the potential parallelism comes from these inner loop nests. But there are some dependencies here, okay, because of these I-1 indexes in this case, okay. So this loop references bi-1 and xi-1. So that means in this case the I loop has a dependency on it. So we cannot parallelize the I loop in this case. And in the second of these loop nests, it's the other way around. We have references to j-1, and therefore, in this case, the j loop is not parallelizable. So that just means we have to be, careful about thinking about which loops are really parallel and which ones have dependencies which prevent parallelization. So this second one's okay because the outermost loop is the parallel one, and the j loop is the one with dependencies. So we don't really have a problem here. We can just do parallel 4 on the outer one. So the interesting case is really this one as to how to deal with this, because if we do so, okay, I'm gonna write code. I'm gonna be brave and write code for you, or at least sketch code for you here. We could, and the simplest thing to do would be to just parallelize. And I'm not going to bother with the data scoping here. It's all pretty trivial. Okay, we do need so everything's shared except temp, except TMP, which is private. So there's nothing too complicated in this one. Okay, so basically we could just do that, and that works. It's correct. But this is one of these cases where now the amount of work inside our parallel region isn't really very big, and this will, if you try this, you'll find that it really doesn't scale very well at all. That's because we're executing too many parallel regions, and the cost of synchronizing at the end of this, because we're executing this very frequently inside this I loop, and there isn't really an awful lot of work inside an individual J loop. So we tend to find that what you find is that it really doesn't scale very well because of the synchronization overheads. Okay, so what could we do about that? Well, one thing you might think about doing that is, okay, let's invert the loop order. Okay, so we could let's let's swap the I and j loops around, and then so now we have the j loop outermost. Okay, so basically do that. Okay. So now we avoid the synchronization overheads, but okay, can anybody see what the problem might be with doing that from a performance point of view? So Felix says memory coherence or some other word for it. Yeah, I think so. Locality is, or so cache locality is really what we're looking at here. So the original code had a nice memory access pattern. So with the J loop innermost, so you have to remember that in C, it's the rightmost index of multi-dimensional arrays, which is contiguous in memory. So when we're accessing multi-dimensional arrays for good cache reuse, we normally want the inner loop to run over the rightmost dimension, and that gives us good sequential performance. But by swapping the loop order around, we've broken that. And if you try this, you will see that the sequential performance gets quite a lot worse if you do that. Well, maybe, okay. You find if you don't have any OpenMP in here, then the compiler might actually be smart enough to swap the loop order back for you. Okay, so if you code the wrong loop order and you don't have any OpenMP directives in it, then there's a reasonable chance that the compiler optimization will actually swap the loop order back to the good one. But once you put the parallel for directive on there, that effectively prevents that compiler optimization from happening. Okay, because now one of those loops is now kind of special and is being transformed by the compiler to be executed by multiple threads, and that prevents it from swapping the order back again. So that's not a terribly good solution either. Okay, so what can we do instead? Well, actually, there is a kind of nice trick here, which is worth seeing, if you like. Okay, so what we can do here is put the parallel region around the outer loop. Okay, so let me put some curly braces in here just to make it clear what I'm doing. Okay, so not strictly necessary, but okay, let's put a parallel region around the outer loop. And now it turns out that, okay, so if we just did that, then we haven't really gained anything because we've still got the barrier synchronization at the end of the J loop. But if you think about the dependencies here, then it turns out that that barrier is not necessary. Okay, it's perfectly okay for every thread, once it's done part of the J loop for some particular value of I, to go straight ahead and execute the same part of the J loop for the next value of I. Okay, so provided we have a static schedule in here, okay, so let's make that explicit. Then we can suppress the barrier at the end of the inner J loop with a no wait clause. Okay, so this is kind of a neat trick to so that what we're effectively doing is parallelizing only the inner loop but without incurring the overheads of having to synchronize at the end of it. So this is a pattern that's perhaps worth knowing about. That it's possible to handle loops where if we have a loop nest and there's a dependency on the outer loop, then we can sometimes use this kind of trick to parallelize the inner loop, but without incurring heavy synchronization overheads. So Felix asks, would nested constructs here? So we can't do nested parallel loops here because one of those loops, that I loop really cannot be parallelized. Okay. We have to execute the I iterations in order. And we can't use collapse either here because we'd end up with a collapsed loop, which itself would still have the dependencies in it. Okay, does anybody have any other questions, either about the practical exercises or anything else in the course material? So Jason says, interested in potential OpenMP GPU programming course. Is that concrete? The course material is under development at the moment, but we don't yet have a firm date for running the course. My guess would be it will be in this sort of sometime towards the end of the year, so November, December time. Okay. So you have to choose between OpenMP and OpenACC. Okay, for a small code with existing OpenMP. Okay, so I would probably advise OpenMP just for the portability aspects. Okay, you probably won't find, well, who knows? Individual compilers may differ in performances in particular cases, but generally speaking, I would probably recommend you go the OpenMP route, just because it's supported in more compilers for more different, particularly if you're thinking about being able to run on different vendors' GPUs in the either now or in the future. Okay, so what's your primary target? Would it be NVIDIA hardware in the first instance? Okay. So, I mean, my experience so far has been that although NVIDIA compiler supported OpenACC before it supported OpenMP, the OpenMP support is quite good for offloading. So if you're targeting NVIDIA compiler on NVIDIA GPUs, then I would probably still recommend using OpenMP, and then you have something that should be also portable to to other compilers and other platforms reasonably well. Yeah, unfortunately, so although latest versions of GCC G-Fortran do support OpenMP offloading, the performance is not great. Philip says, you mentioned an advanced OpenMP course. We have plans to host that one again. I don't think we've got one scheduled at the moment. It would probably be, so we kind of usually run these around 6 months apart. So I'd expect, but I can't guarantee that we'll schedule one probably early next year sometime. But if you're, if you don't want to wait that long, then there are instances of the course on the past course materials page on ARCHER2 with video recordings. So if you don't mind going down the self-learning route for that, then that's a possibility for you. What about synchronous MPI course? You mean an introductory MPI course? Okay, so again, I don't think we don't have anything scheduled. There is a self-learning MPI course available, as there is for OpenMP as well. So you can sign up to that. Otherwise, yes, there'll probably be a live run somewhere. Good. Anything else? Okay, so just a couple of things then before we finish. So if you've been using the temporary accounts for this course, then those will get deleted in a couple of weeks' time. So if you want to save any of the work that you've done, then please remember to copy your files somewhere else before then. And also it would be really nice if you could take a few minutes to fill in a feedback form for us for this course. Okay, I will post the link in the chat. There it is. And we'll also send an email reminder around in a few days' time, probably. In case you don't feel like doing it right now. It'd be very useful just to get some feedback. So not just on the content of the course, but also on this format with that that we've done this course in having these having the material spread out across different mornings over a couple of weeks, and this separate session today to go over the practical exercises. Would be interested to know whether that worked for you, whether you found that helpful, or whether that was just annoying and you'd have rather just blocked out like 2.5 days to do the course in a one. Okay, so if there aren't any further questions, then I'd just like to say thank you very much for attending the course, asking interesting questions. I hope you found it useful, and hope to maybe see you again on other training sessions.